is Science 2016, paper 1. Suppose this is in 10. So we'll run through this paper together, and then when there are questions, you put up your hand at the end of the lesson, the presentation will be sent. So question 1 says, question 1 is coming from measurements. It says the diameter and the length of a thin wire approximately, so we have the length of 50 centimeters as well as the length, approximate length, 15 centimeter in length, is measured as precisely as possible. What is the best instrument to use? So we're talking about the length as well as the diameter. The key thing here are the thin wire as well as this distance. So this distance, 50 centimeters, the best that we can use here is a meter rule. We can use a meter rule to measure this 50 centimeters, and because it is very thin, I would suggest that we go for the micrometer screw gauge, because the micrometer screw gauge has the best accuracy and precision as compared to the vernier caliper. So we can settle for this. B, question 2. Which of the following is the SI units for measuring time? Time is measured in seconds. We can also confirm with the speed, which is equal to distance over time. Distance is measured in meters, over time is measured in seconds. That's why our speed units are meters per second, because these seconds, they represent our denominator in the formula, which is time. Question 3 and 4. Questions 3 and 4. Let's see what we have. If we can even enlarge the way it was, it's okay. So 3 and 4 are here. Question says, the diagram below shows a speed time graph for a car. So we have this car which covered the 2 seconds to move. It covered 2 seconds to move at the speed of 5 meters per second. Here the speed increased up to B exponentially. It kept increasing but with a reduced acceleration up to C. And at this C here, the object stopped increasing its speed and it started reducing. And remember, when we have a point here, what we know is that in mathematics, that the gradient of a function at a turning point is 0. And in our case, our gradient, which is change in velocity over change in time, which is dy dx, this is acceleration. So we can clearly see that at this point here, the object was moving with a 0 acceleration, because at this point here, the object was moving with a constant acceleration. Now, what is the question saying? At which points, so we're talking about points, at which points is the car moving with 0 acceleration? At this point here, the graph, we can see that it was horizontal. So A, at point A, the car was moving with a constant velocity, which is 0 acceleration, as well as point C. And therefore, these two are the ones that are having a combination for the perfect answer. Question number 4. when a nut and a bolt are difficult to undo, it is easier to turn a nut using a longer spanner. This is because the longer spanner gives a larger turning point. So this is moment. Moment is equal to distance from the pivot up to the point of action multiplied by force. So meaning when the distance is long, for the same amount of force which is applied, when the distance is increased for the same amount of force, we find that the turning point of an object at the pivot, which is called the moment, is increased. And therefore, when the distance increased for the same amount of force which is applied on the longer spanner as well as a shorter spanner, we'll find that a longer spanner will give us a larger turning point. So here the answer is C. Move on. 5, 6, and 7. So 5 says a body moving with a speed of 30 meters per second and has kinetic energy of 1,800 joules. What is its mass? So it was the other day I was saying that whenever you see that certain physical quantities, a certain physical quantity has already been given, so we have our kinetic energy, which is already indicated here. So meaning, write the formula for kinetic energy, and then you substitute the parameters that you have. So it's mv squared, and then divide by 2. Now, from the information that we have, our kinetic energy here is given, which is 1,800. 1,800 is equal to the mass, we don't know. Therefore, the velocity is 300. So we're going to say 300 squared multiplied by the mass, then we divide by 2. Now here, do not divide the 2 and the 30 because that 30 is squared. So meaning the best thing that we can do to this question, first of all, is to expand it, or maybe we can cross multiply. And when that is done, what are you likely to get? What you have is this. When that is done, we're going to have, if you want, you can cross multiply here so that this 2 multiplies 1,800, and then this 30 meters is squared. So when you square these 30 meters here, you're going to have 900. So you're going to have 900. M stands for the mass, which is equal to, now this 2 multiplies 1,800. So I'm going to say this 2 is multiplying the 1,800. 1,800. At this point, we can divide by 900 here so that we leave our M as a subject of the formula, multiplied by 900 here also, so that when this cancels, we'll have our M, which represents the mass that we are looking for. This is 0 cancels with that 0. This is 0 cancels with that 0. This 9 goes into 18 2 times. Therefore, these are the only numbers that are multiplying to give us our mass. And that therefore our mass is 4 kilograms. So this was the mass of the object, which was moving at 30 meters per second for it to possess the total kinetic energy of 1,800. That was the answer. And then question 6. Which of the following properties of a body is affected due to the change of gravitational field? Now, this gravitational field actually is G. Let me write from here. This gravitational field is actually G. Now, which one depends on the value of G. Is it the mass? The amount of matter in an object does not depend on the gravitational field. The temperature does not depend on the gravitational field. Actually, the temperature does depend most of the times on the altitude. Remember in grade 9, they told us that the higher you go, the cooler it becomes. So certain places are colder and other places are cooler than the others because of the height of those places above the sea level. The volume, the amount of space occupied by an object does not depend on that. Yet the weight is a product of mass multiplied by the gravity, meaning if this value changes, the weight will also be affected. And therefore, the physical quantity which depends mostly on the gravitational field is the weight. Question 7 says, which substance A, B, C, or D is a liquid at 20 degrees? So meaning for this object to be, for this liquid to be for this substance to be a liquid at 20 degrees Celsius, we expect to have its melting point. The melting point must be lower than 20 degrees, meaning this object is this substance is supposed to melt before the temperature gets to 0 degrees. And its boiling point should be actually way bigger than the 20 degrees. That is what this substance. These are the clues that we can have. Remember, if water is, let's pick water. If water 25 degrees Celsius is a liquid, meaning it is supposed, and of course we know that it melts, the ice melts at 0 degrees and it boils at 100 degrees. So we can see that the temperature at which this substance is existing as a liquid is between its freezing point as well as its melting point. So meaning we'll just come and compare here. These two values are wrong because these two values melting points are bigger than the 20 degrees, which is contradicting this statement. So these two are wrong. We'll also go to the boiling point. The boiling point that we are looking for must be bigger than 20 degrees, and this thing is smaller. So this one also is disqualified. Therefore, the melting point less than 20 degrees, the boiling point above the 20 degrees. Therefore, the answer is B. Can move on to questions 8 and 9. So questions 8 and 9 say, a boy strikes a rail with a hammer to create a sound along the rail. A girl listens with her ear against the rail. A second later, a girl hears a sound through the air. So what was happening is that this boy here is the one who was striking the hammer on the rail so that sound could be heard, and sound was traveling in this direction to a point where the girl was hearing it. A second later, we're told that this girl hears sound through the air. Somewhere kwinangu sound yambeka. So the question is, how long will it take for the sound to reach the girl through the rail? So because she heard it a second later in the air, that's when she heard it, and we know very well that sound travels faster in solids compared to liquid, and it travels faster in liquids compared to gases. So we expect sound to be heard on the rail for less than a second, because the speed in the rail or on the rail, which is a solid, is supposed to be faster than that on the air. So expect it to be less than a second. Because the speed, the speed in the solid travels faster than in the liquid. Question 9. Which of the following waves belong to the same class? Which of the following waves belong to the same class? Which classes are they? It's transverse waves as well as longitudinal. So if we pick on longitudinal waves, we just expect to have longitudinal waves all along. And if we pick on the transverse waves, we expect to have transverse waves all along. So light, transverse, radio, transverse, water nipples, transverse. So these belong to the same class. Let's try here: sound, longitudinal, radio and light, transverse. So this does not belong to the same class where these two belong. Microwave, infrared are both longitudinal, sound are both transverse, sound is longitudinal. It refuses. So the same thing happens here. The appearance of sound makes it impossible for these three answers to be correct, because sound is actually longitudinal. Sound is longitudinal. The rest of them are falling on the transversal class. So therefore, A, which contains only transverse waves, is the answer that we are going to settle for. We go to 10 and 11. 10 says, water waves are produced with a frequency. So we have a frequency of 5.0 or just 5 Hz. So it means the number of waves that were being produced per second was 5. By hitting the water surface with a tip of a pencil, with the tip of a pencil, and this person was very fast, that 5 waves could be produced per second. And if the water travels, the speed, it covers a distance of 30 meters in 6 seconds. What was the distance that was covering a single wave? So first of all, we need to understand that speed is equal to distance over time, and our distance covered here, according to the question, was 30 divided by 6, and this gives us 5 meters per second. So the speed was 5 meters per second, and the formula is speed is equal to frequency times wavelength, which is lambda, times wavelength, which is lambda. So our speed here is 1, is equal to, our frequency is 1 also. Oh, the speed here is 5, the one that we just found here. And our frequency is also 5. Frequency is also 5, which is multiplying with the lambda. And we can see that when we divide by 5, the wavelength here was 1, which you can say 1.0 meters per second. So the wavelength was 1 meters per second, or rather was 1 meter, because the wavelength is a distance between two identical points. Sorry. So the wavelength was 1 meter. So what does it mean? It means that this wave was moving. The distance from here up to here was 1 meter. And this wave was moving at 5 meters per second. So meaning it was covering 5 meters for a single wave. So this distance is 5 meters, and it was also covering 5 meters each second that passes. That's what it means. So we can now go to question number 11. And question number 11 says, the diagram below shows a beaker of water containing a red crystal, which slowly dissolved. A gentle heat was applied below the crystal. So the heating was done right from this end, and we are talking about heat transfer. So what does it mean? It means when this heat was being applied here, heat was being conducted, was being transferred through the base of this vessel by the method of conduction. This heat was distributed throughout the water by convection. So the red color is seen to rise. The red color was rising above there. What is the name of this process? So the process by which the heat was being transferred now throughout the water, that's the only way the red color would be seen rising. It's because it was in the liquid. And therefore, the method by which this heat was being transferred is convection, because it is through the liquid. It was through the liquid. And if we can go to question 12, we can reach 20 before we run out of time. We can actually finish this paper, section A. So the question says, which characteristics? So we have sets of characteristics that describe an image formed by the mirror. So first of all, I was trying to crack a joke with you guys when we're in grade 11, where I was saying at times we should get worried of what we look like. Why? Because no one has ever seen his face. The only thing that we rely on that's because we look at the mirror. And what actually the mirror gives us is the image, not the actual object. So in short, you've never seen the true image of your face. You've never seen the real object, which is your face. You have just seen the mirror giving image. And that image actually, it is not real. So if it is not real, it's virtual. It is virtual and it is virtual. Then what else can you say? If it's not virtual, then it is not real. So this is wrong and this is wrong. They are virtual, they're not real. Now, actually, the size of the image that you see is equal to the object. That's the reason as to why if the mirror is here, your face is here, the object, the image actually, if this is the image and this is the object, that is you now here, meaning you are going to see yourself on the other side. And the distance between the mirror and where you are and the distance between the mirror and the object are actually equal. And even the size of the image and the size of the object are the same. And that's the reason as to why when we draw closer to the mirror, we see our faces becoming bigger, because this image is also coming closer to the mirror as you draw closer to the mirror as well. As you pull yourself away from the mirror, you see that even the image starts looking smaller, because the size of the image is equal to the size of the object. And therefore, here where it says it's smaller, it is wrong, but it is upright. It is upright in such a way that when you are standing here, the way the image will be seen on the other side will also show the position in which your body is. If you're standing upside down, even the image there will be seen upside down. If you're standing upright, even the image will be seen upright. So it's virtual, it's also upright. It's not real. Thoreen says the diagram below shows a ray of light. This is the ray, which is an incident ray, which is going toward the boundary at 40 degrees. What is the angle of incidence and the angle of reflection? So this is a mirror, and we also have to draw a line that meets the boundary at 90 degrees, and this is called a nominal ray. So because it's at 90 degrees and we are already given this as 40, we expect here to have a 50 degrees. And because what is happening is bouncing back, this one is also 90 degrees. So when it bounces back, the size of the angle which is here actually is also 50. The angle which is actually here is also 40. So during reflection, the angle of incidence is equal to the angle of reflection. So if what we have is 40 is 50 here, we expect even the other one to be 50 because they are equal to each other. So the answer here is D. The angle of reflection and the angle of incidence are both equal when the object that we're dealing with is a mirror and we are talking about a regular reflection. So if we can proceed, if you have questions, guys, just put up your hand. I'll quickly go back. We look at 14 and 15. 14 here says, which row describes the case with which iron or steel can be magnetized or demagnetized. Steel is an alloy of iron and carbon. So steel, whether mild steel, stainless steel, is an alloy of carbon and iron. So because this is an alloy, why do we alloy elements? It's because we want to improve on their resistance, durability, among others. So we expect this steel to be harder as compared to alloy, to the actual element, which is iron. Now, because it is hard, you'll find that this steel, when you want to make it a magnet, when you want it to possess the magnetic property, it takes a lot of time because it is a hard magnetic material. Hard as it is to magnetize it, it also takes time for it to lose its magnetic property. So the question here says, which row describes the case with which iron or steel can be magnetized and demagnetized? Here there was a repetition of answers. Iron is easy to magnetize and easy to demagnetize. So these two were correct answers. Iron is easy to magnetize and easy to demagnetize, while steel is difficult to magnetize as well as difficult to demagnetize. So it takes a little bit of time for steel to lose its magnetic properties once it possesses them, or magnetic powers. And speaking of magnetism, 15 also is talking about magnetism. A permanent magnet is placed. So this is a magnet. Now we see how it is to magnetize. Oh no, so I was talking about plotting of a magnetic compass. So a magnet, permanent magnet, which is still actually, which is used because it doesn't lose its magnetic property that easily. So they plotted a compass, put a magnetic, permanent magnet like that, flat on the surface, and the plotting compass is plotted on the dot as shown in the diagram. So this is the permanent magnet that we have here, and we have the compass which is plotted here. So the only thing that they wanted to show, they wanted you to tell is how do magnetic field lines move? Do they move from the north to the south, or do they move from the south to the north? Actually, the magnetic field lines move from the north and they entered through the south. So if the magnetic field, if the compass was plotted here, we expect a deflection towards the south. So this was the right direction in which the compass is supposed to deflect, because the magnetic field lines, they enter the magnet through the south and they come out through the north. So the answer here is C. 2 minutes remaining of time. We can do maybe just 7:16 so that I leave with a minute for you to ask. A sphere, a positively charged rod. This is positively charged. As we can see, we have positive charges all around it. Is held close to, but not touching, an insulated metal sphere. So when they say an insulated metal sphere, actually this is neutral. The number of positive charges as well as the number of negative charges are equal. And when this happens, by the nature of bringing these charges closer to each other, the reason as to why they were not touching, they never wanted these charges to cross from the rod into the sphere. They just wanted to have a fundamental first law of electrostatic in which the charges rearrange. So when that happens, because this is a positively charged rod, we expect all the positive charges that are around here to deflect, or the term that we use is to repel. They go away from these fellow positive charges. So what do we expect? We expect my positive charges to be this side. We expect them to be this side. And all the negative charges that were in this sphere, we expect them to be attracted towards the negative charges, toward the positive charges. So we expect it to be this way. Now, because this is neutral, the number of positive charges that we have must be equal to the number of negative charges that we have. And this rearrangement of charges corresponds to what we have on D. So D was the answer. Within a minute, any question? Was there a question that I did not explain well? Is there any question that I need to go back to? Please, you ask, because we are remaining a minute. Guys? Yes, Helen?
Can you please explain 16?
15?
16.
16, okay. So here is